So first of all, let me I share my screen. Let me share my screen. Can you see my computer screen?
No, we don't.
Not yet.
Okay. How can I share my screen? How can I share my screen?
I think you can hit the button share on the top right of your computer or PC next to delete button, I think.
There's a share button beside the microphone button, Prof. Shufeng.
Yes, but I cannot find the share button.
It's called the open share tray, if I'm not mistaken. It's the same then.
I'm sorry. Maybe I cannot share my screen. Oh, sorry. How can I? Maybe I can send my PPT to you. You share the PPT. I speak through my computer.
Yes, can Prof.
I cannot find the share button. Really sorry.
Prof, can you try Control Shift E?
Control C. Control C.
Control Shift E.
Control Shift and the E, right?
Yes. Is there any windows open?
Together, the three button.
I think we can help Prof. Shufeng to share this slide. Maybe.
You can send the slide to us.
Control Shift and E, right? Okay. I do not know. I do not use this software before, so.
Shamin can give emails, so Prof can send the slide to you. Okay, Prof, you can, if you cannot share, you can send your slide to email in the chat box. shamilsaad@um.edu.my.
Okay, I sent the PPT through through my email.
Yes, you can, Prof. You can send to the previous email, PRCUM. Also can. There is one email that we contact you with, then you can
Yes.
send there.
Okay, I send you the email.
Yes, okay.
Okay, please check your email.
Okay, checking now. Wait a moment. Prof, we did not receive yet. You sent it to which email?
Yes, I sent to the senior.
It's in your email, Shamin.
Senior.
Not yet.
Check.
Haven't received yet.
You received it?
Not yet. I've checked into spam also. There's no.
Okay, I send you again.
Okay, thank you.
Okay, I just sent it to the email you just sent me.
Yes,
Okay, I tried to download first. I received the email. I tried to download first.
Maybe it's too big. It's about 70 million bytes.
The file is quite big, so it takes some time to download it first. We are currently downloading your slide, Prof. It may take a while, about a few minutes.
Didn't you receive my email?
Yeah. We did receive your email. We are currently downloading your slide.
We are now downloading your file, Prof. So hopefully in a few minutes, we can share your slide.
Okay, now you share my PPT slide.
Can you see the slide? I've already
Yeah,
shared.
yeah, I can see.
Okay, right.
So you please control for me, okay?
No problem at all.
Okay.
Can do it.
I'm awfully sorry for I should do it before the conference. I'm sorry. Anyway, I should first thanks Professor Harris, who invited me to take part in the conference, and also thank University of Malaya and to give me this chance to share my research. So maybe my research interests are a little bit different from the conference title, but we use the fiber laser also. So it's also a kind of optical fiber use domain. So my research are mainly focused on the research and application of laser precision processing technology. I come from Qingdao University of Technology. So my name is Shu Fengsun. So next. Please, next slide. So first, let's see the background of our research. The global market for laser material processing systems in the 2021, the total is about 21 billion US dollars. And in 2020, it's only about 17 billion US dollars. So it increased 22%. And by application, the high power processing, such as high power laser cutting and welding, they account for 47%. And then the micro electronics processing is about 24%. And the low power fine processing is only about 18%, and the marking is 11%. So please next. So in 2021, 65% of the demand for laser processing systems is located in Asia. Only China account for 35%, and other Asian countries 30%. So Europe is 19%, and America is 16%. So the main domain of the laser processing market is in Asia. So please next slide. So the application of laser precision technology is widely used, such as welding and cladding, cutting and drilling, integrated optics, additive manufacturing, and the surface modification from macro scale to micro scale and nano scale. So please next. So my report is 3 parts. Part 1 is laser processing micro holes on blade, and part 2 is laser processing scattering dots on light guide plate, and part 3 is laser shaping and parallel processing microstructures. So please next. The engine is the heart of the airplane, and the combustion chamber of the engine the temperature is about 2000 centigrade. So the turbine blade work in the combustion chamber, so it should work under 2000 centigrade, the high temperature. So there are two important technologies for turbine blade. One is it uses heat-resisting material, such as silver alloy can work under 1100 centigrade. Fiber-reinforced ceramic composite material can work under 1650 centigrade. So no material can work under 2000 centigrade. So another important technology is air film cooling technology. That means on the blade, there are many microstructures processed. During the turbine blade working, the air will pass through the micro hole and form air film to keep the heat away and cooling the turbine blade down. So the micro hole processing is very important. Next. There are many problems for the micro hole drilling, such as if we use a drill to drill the micro hole, the drill will wear and fracture, and there are also burr on the edge of the micro hole. For EDM, only conductive materials can be processed. There are also recast layer on the edge of the hole, and it also generates heat-affected joint. For ECM, also only conductive material can be processed, and a low processing efficiency, but it can got a very smooth surface. The laser processing also will generate recast layer and a heat-affected zone. So our research will combine the ECM and the laser processing. Please, next. So we first researched the femtosecond laser processing micro hole on nickel-based silver alloy. First, we researched the scanning path of the focus. The straight line, spiral line, and the concentric circle scanning from inside to outside, and the concentric circle scanning from outside to inside. So number 3, the concentric circles scanning from inside to outside. The processing quality is a little bit better than the others. So please next. And the laser pulse energy is also an important factor for the micro hole processing. So we also find that the laser pulse energy is about 100 microjoule is the best. So please next. And the focus overlap rate we also optimized. So 95% at 300 millimeter per second is the best compared with the others. So next, please. And we also optimized the processes with 2-step method. The first step is drill the micro hole with a through hole. The second step, we will enlarge the micro hole and repair the wall of the micro hole. So this is better than one step because the hole diameter and the surface are improved. So please next. And we also analyze the surface of the microhole and on the top of the microhole. It means that in the wall of the microhole, the oxygen content is higher than the other places. That means during the laser processing, the oxidation is serious. So please next. And we analyzed the wall of the microhole and the edge of the microhole. So it looks smooth, and there's no serious oxidation or recast layer on the wall or on the edge of the microhole. So please next. And we optimized the parameters, and we processed the microhole with a little bit better quality for the inlet and the outlet of the microhole. It looks better. So please next. So before we use the femtosecond laser to process a microhole, but for the nanosecond pulse laser, the heat effect is obvious. So we present a hybrid processing method of laser high temperature chemical dissolution processing. We use laser processing to drill the microhole, and simultaneously we use the laser to warm up the chemical liquid in the microhole to accelerate the dissolution of the oxide layer. So we can get a higher surface quality. So that means laser processing is high efficiency, and chemical dissolution processing can obtain high surface quality. So please next. And we compared the laser processing and the laser high temperature chemical processing. We can see on the wall of the surface, if the laser processed in the air, the recast layer is obvious and serious. And for the laser high temperature chemical processing, the recast layer is dissolved. So please next. And we say the ceramic composite material can work under 1650 centigrade. It will be used to make turbine blade in the future. So we also do some research on this material to drill the microhole. This is the structure of the CMC silicon carbide material. Please next. And this kind of material, because it's not a metal material, so it is difficult to processing than super alloy. We also use two-step method to drill the microhole, the nanosecond fiber laser, high temperature chemical processing through hole. And the second step, we also enlarge the microhole, but it's difficult and the quality is not so good. Please next. So we change another laser, the ultraviolet nanosecond laser processing. So this kind of laser is better than the nanosecond fiber laser, because this kind of material is non-metal material. So we can see the microhole is better than the nanosecond fiber laser. Please next. And we also analyze the EDS energy spectrum analysis. We can see on the wall of the microhole, the oxygen and the carbon elements are also different because the foreign reaction will generate during laser processing. The carbon and the oxygen to generate CO and the CO2, and the silicon and oxygen will generate silicon O2. So next step. So part 2 is laser processing scattering dose on light guide plate. And next. The liquid crystal display have many advantages, such as less power consumption, low radiation, ultrasound, and stable performance. So it is widely used. Next, please. This is the composition of LCD. So the liquid crystal panel, and the other is the backlight source module. In the backlight source module, the light guide plate is a core part for the backlight module. On the surface, it should be fabricated a lot of scattering doors to change the LED point light source to a uniform surface light source. So please next. Before ink printing technology is used to fabricate the microscattering doors, there are many problems. So to overcome the above problems, we use laser processing technology to replace the ink printing technology. So this is the processing method. Please click this figure. Please click the. Okay, this is the equipment we made to process it. Please click this screen. That video. Cannot play the video. Yeah, this is the workshop. The equipment we made for a factory, now they use the laser processing to fabricate the light guide plate. So please next. Okay, please next page. This is the light guide plate, which are process the microscattering dots on the surface by laser. And then this is the brightness uniform detection, and this the backlight module made by a light guide plate with scattering dots processed by a laser. And the last figure is the workshop of RGP processing. So please next. And part 3 is laser shaping and parallel processing microstructures. Next, please. Okay, because for the single laser beam serial processing, the efficiency is very low. So how to improve the processing efficiency is important. So we researched the laser beam shaping and the laser beam splitting to improve the microprocessing efficiency. So next, please. And figure A is the schematic diagram of our laser parallel processing technology. And the figure B is the 3D model of the equipment. And 3C is we developed software for computer generated hologram. And the figure 4 is the equipment we set up in our lab. Next, please. And based on the fractional order Fourier transform principle, we use the Gauss beam and CGH. We split the laser beam to 36 beams, and 36 dots are processed simultaneously. Next, please. And we also use the laser splitting technology to got a symmetric dot array to process, and we also generate a symmetric dot array, such as 1921 and 2021, and the Chinese letter to process at the same time. So next, please. And the other, such as the Wi-Fi icon, and we use the zero order light to process the big point, and then the other point also splitted by one laser beam, so we can process the dots simultaneously. And the other kinds of the smile face and the Chinese letter, Qingli, the Chinese letter. So we can design the light, the aim light, and we also split the laser beam, and we process the dots array at the same time. So next, please. And also 3-dot array. Before we processed on the same surface. So now this is on the three surface, the surface 1 and the surface 2 and the surface 3. So there are different numbers of dots. And this is the QT dot array, also on 3 different surface layer. So next, please. And we also do some laser beam shaping, such as the triangle, square, and the pentagon shaped laser flat top light laser design. And we also generate the holography, and we process this triangle, square, pentagon, and also, so next, please. And we also split the laser to 7 layers, 7 different focus, and we processed in the glass. We can see the 7 layer, 7 different focus can processed in the light in the glass. So next please. So also process in the glass for the grating. And figure A is we can see the grating is obvious, and the figure B means that it's transparent from different angle direction. We can see it's transparent, and the figure C we can see also there's a rainbow strips. This is the same glass we processed inside with the 3D grating. So next please. And we also researched the laser beam cutting the glass and the silicon. This the stealth cutting the glass and then the silicon. Next please. And we also do some trifocus cutting, multifocus cutting. You see, trifocus cutting, multifocus cutting. Because it's a stealth cutting, so the cutting edge, the quality is very good. So next please. Okay, thank you. So I'm sorry for inconvenience.
Right. Okay. Thank you very much, Prof. Shufeng San. Very interesting presentation. You did a very good work. So for that, I open any question from the audience, if there is any. Any question from the audience?
Yeah, Doctor, can I ask a question?
Yes, please.
Hello, Dr. Shufeng. I wanted to ask more about the holes that you dig for, not dig, I mean that you drill for the turbine or the aircraft turbine. You said it was drilled under a dissolution, correct?
Yes.
It was submerged in a kind of solution to prevent it oxidizing when drilling, is it?
Yes, you're right.
My question is, can it be done under vacuum or inert atmosphere such as nitrogen? Does it can it result in the same effect, or will it result in a different effect?
In the air, not in the vacuum.
No. I mean, if we can it be done under vacuum or nitrogen?
It's nitrogen is okay. Nitrogen, not a vacuum.
Or vacuum cannot, is it?
Yeah.
Okay, understood. That is all. Thank you.
Okay, thank you.
All right, maybe one last question, if there is any. Any question? So if there is no question, I would like to thank Professor Shufeng San for your presentation. So have a nice day, Prof. And the audience, maybe you can use the reaction button to applause him. All right, thank you, Prof.
Yeah.
So we move to the next session, which is the presentation by Professor Tariq Muhammad. So Professor Tariq, are you here? Are you ready for your presentation?
Yes.
Welcome, Prof. Welcome.
Yeah, thank you.
So the next session will be the presentation by Professor Tariq Muhammad. He's from Laser Institute for Research and Applications, LIRA, from Beni Suef University, Egypt. So I read a short biography about Professor Tariq. He's received his PhD in laser physics from Stockholm University in 2003. Following his employment as an associate professor at Beni Suef University in Egypt in 2009, he became a full professor of laser physics in 2015. From 2004 to 2009, he worked as a senior scientist at the Riken Institute in Japan. He worked at Texas A&M University's Attosecond Laser Laboratory from 2009 to 2012. From 2013 to 2015, he was a senior scientist at the Extreme Light Infrastructure Attosecond Light Pulse Source in Hungary. In October 2016, he was appointed as a dean by Beni Suef University, Egypt, to supervise and lead the Laser Institute for Research and Applications, LIRA. He had also published over 70 papers in international scientific journals and conferences. So without further ado, I would like to, you can present now, Prof. Thank you.
Okay, thank you. I'd like to share my screen first. So it's working?
Yes, Prof.
Is it okay? Okay. First of all, I would like to thank you for the introduction. And I would like to thank Professor Harris for giving me the chance to participate in the conference. And I am really glad to join the conference. And over yesterday and today, I was enjoyed the talk. So I'm sure by the end of the day, it will be a successful conference. And before I start my scientific talk, I just would like to show you some fun fact about ancient Egyptian people. So we start with the map, Egyptian map. So the ancient Egyptian people live around the river, and we still like that till now. And here is my city. It's called Beni Suef city. It is located 120 kilometers south of Cairo, and my university in Beni Suef. I grew up in a small village. It is around 20 minutes to Beni Suef city, but currently I'm living in Beni Suef. Egypt was, I have in my city a very famous pyramid. It's called the Maydoum Pyramid. And this is built during the fourth dynasty, ancient Egyptian family. It is around 2,600 old, BC old. And I found also some thing about ancient Egyptian people. We have another pyramid called Sesostris II, and around this pyramid they found some mirrors and made by polished copper, bronze, and copper tin alloy. So it looks like they were the beginning of optics field. This was around 1900 BC. Also, the beginning of light-based therapy was by ancient Egyptian people around 1500 BC, and we found this in the papyrus. They use the light like base therapy tools, sunlight. Then come to my talk. My talk will be in two parts. The first part will be around Laser Institute, quick brief history and research laboratories and the research activities. And second part, I will focus on one of the research activity at LIRA, nonlinear optics research, and I will conclude by the end. Here is the organization of the institute. We have 6 departments, most of them around laser, studying laser and laser applications. And the construction of the institute started 2013 and ended by 2016. And here is the final landscape of the LIRA Institute. And this is the side view, and this is the top view. And in parallel to the construction, we prepared laboratories, lasers, and the other equipment. And once we finish the construction, we have the equipment. So we have nanosecond laser system, 2 nanosecond laser, quanta ray. This is deliver 1,500 millijoule per pulse at 1064 nanometer, and we have a new one, another one. This deliver 2,500 millijoule per pulse at 1064. Also, we have pulse dye laser. This could where we could tune the wavelengths from UV 390 to 1,000 nanometer by changing the dye. And we have two femtosecond laser system, MiTi and Inspire. So the MiTi was made by 2 lasers. One of them called Millennia is CW laser and give green light 532, and Tsunami. This is a tunable solid state laser, and we could tune the range from 700 to 1080 nanometer. And average power 2.9, pulse duration 100 femtosecond, and 80 megahertz repetition rate. This is mainly based on titanium sapphire as active medium. So they merge 2 of them together, the Millennia and Tsunami. And finally, we have just one box. And this box, we have these 2 lasers. It's very compact and it's very nice femtosecond laser system. The other one is Inspire, and Inspire also is a femtosecond and pumped by MiTi, and from the Inspire we could have 4 output, and the 4 output covers range from 345 to 500, 2,500 nanometers, to start from UV to mid-infrared, and also repetition rate 80 megahertz, and the pulse duration less than 100 femtosecond. This laser mainly based on nonlinear optics, and so made by nonlinear optical crystal to like OPO crystal and second harmonic generation and third harmonic generation crystals. So it's very good one. Then we have some spectrometer for doing laser spectroscopy, like laser-induced breakdown spectroscopy, laser-induced fluorescence spectroscopy. So we have 2 spectrometers that could cover from 200 to 1,650 nanometer. We have also lab for laser application biology, equipped by biological equipment like laminar flow, CO2 incubator, centrifuge, and microplate liquid nitrogen for keeping the organisms and cells. And we have laser application microbiology, and we have unit, microscope unit, also most of this for the biologist. And we have a lab for training student, like diploma student. We have diploma student. First, the student come from finish 4 years study, like in Faculty of Science, Faculty of Engineering, then come to the institute to study master and PhD. And for the master or the PhD, he should have some diploma. And during this diploma, we have training lab. And this is the lab about electronics, optics, and light. Here, researcher, current researcher in institute. We have a senior researcher like biologist, some people from the medical field, and we have PhD and master student, most of them like permanent position at the institute. And we have collaborator from outside Egypt. We have some people from Harvard, from Stockholm University, from Texas, and from France. And I have discussed with Professor Harris and a few months ago, and we'll have in the future collaboration. Here's Lira Manpower. I was a member, research staff, and administrative staff, faculty member growing with the time. And this here shows where we collaborate. So most of this we did it in the paperwork, and some of them active, and still some of them will be activated in the future. About the scientific product, as I mentioned, this is a young research institute, so we start small publication, and by 2020 we reached something like 51 published paper in a good journal. So it's growing, is not so bad with the time. And here is the research direction as an institute. We have like 10 research directions. We didn't start by 10, we start one by one. And with the time, we increase this directions. And I will show quickly some of these research directions. So for example, we have laser material processing. We do some nanoparticles. So we try to use the nanosecond laser, YAG laser, to control the size and shape and concentration of some of nanoparticles like silver, gold, zinc oxide. And we are currently trying to do metal alloy nanoparticles. So this nanoparticle have different applications like antimicrobial effect, antibacterial effect. So the group, biology group, they use, once we create this one, they use it in the biological application and also in medical application at the institute. We try also laser-based micro application. We try to do micro holes in some samples using femtosecond laser. So this is the setup for laser ablation to create nanoparticle, very simple, and we use YAG laser. And this is laser-based microfabrication. We use femtosecond laser to create some nanoparticle, micro holes. So we reach view micro hole size and very symmetrical hole. Here is some publication. We did something in optic communication, and we have another publication about novel surface topography and the micro hardness characterization of laser clad layer on TC4 titanium alloy using laser-induced breakdown spectroscopy. This is already accepted in one of the good journals, Springer. And we have the other direction on laser application in microbiology. We have different subjects, like bactericidal efficacy of femtosecond laser against most common bacterial pathogens, and laser-based bacterial antivirulence therapy, and also study antibacterial effect of laser photoactivated quantum dots, and laser application in reducing food poisoning with bacterial pathogens. And here we use femtosecond laser quickly. This is a simple setup. And we have in the 96 well plate, we have bacteria sample here. So we expose this to the laser, and we try to change all the parameters of the laser, like power, like wavelengths. We use the benefits from this laser that we can tune the wavelengths, so we could know exactly the optimum parameters that could inhibit such bacteria, and also the exposure time. Also, we use also one of the directions of biology. We did laser-based photodynamic therapy. Also, we use femtosecond. So we know once we have some wound in the tissue, the bacteria go through the tissue, and the immune system try to protect this, but sometimes doesn't work. And lastly, the bacteria go through the blood. And one way to protect after wound is use light, and we try this as an institute. So the light have two benefits. One of them is to killing the bacteria, and the other thing is induce or quick the speed up the healing. So we did this extensively at the institute. Here is a physical picture of laser-based photodynamic therapy. It helps in creating oxidative oxygen species, and yes. And here's the setup for doing this one. So we have the femtosecond laser, and the beam go through some mirror and come here. Then after that, go to the bacteria. Here we publish some paper over this one, and the goal from also the goal from this work is to after we study all the parameter and we know the optimum parameter, the goal also is to do a small laser that could be used by maybe the patient or doctors in the hospital. Also, we have laser-based spectroscopy group, and we do laser-induced breakdown spectroscopy for bacterial identification and quantification. We do laser-induced fluorescence spectroscopy for blood biomarkers detection and analysis, laser-induced fluorescence spectroscopy for cancer detection and diagnosis, laser absorption spectroscopy for breath analysis. This will be like a replacement of blood test. This subject in the future. So we use a laser to identify the diseases, and instead of using a blood test. Here is the setup for laser-induced fluorescence spectroscopy for blood biomarker. So the femtosecond laser bulbs come here and go to the sample, and we could detect the emission from the sample, and we analyze this one. We could know exactly the concentration and the biomarkers. And we publish this article, rapid monitoring of serum albumin as a biomarker of liver and kidney disease using femtosecond laser. It is new, it was not done before, such work. And also we use laser-induced breakdown spectroscopy for bacterial identification. Here is the bacteria, would be here. And we try to get fingerprint from, we use different bacteria together to get different, for each bacteria we have different emission light. So we could, if we have a mix from bacteria, we can identify them using laser. Also, we have something in dental medicine. So we, some topics. We use a laser also to map the dental layer. So we have focused the laser on the dental, and we record the emission using spectrometer, and we could know exactly which element we have in the dental. And as you can see here, we could also know exactly calcium and magnesium, identify iron, sodium, phosphate, potassium, and we could know exactly the abundance of each element, was it normal or not. Also, we have laser application, as we have laser application microbiology, we have laser application biology, and we have 3 topics. Here we use the laser, try to use the femtosecond laser for treatment organ like liver, kidney, and fibrosis, like liver fibrosis, also studying the behavior of cancer cells. Also, we have some work on liver laser therapy for wound healing. And there is a simple setup. We have the laser, femtosecond laser goes through some optics, and then we go to rat and like animal model. So we did some work using a femtosecond laser attenuates oxidative stress in inflammation and liver fibrosis in rat. And here we induce liver fibrosis in rat, and we send the laser. We use 800 nanometer, which can go through the skin and reach the liver without any surgery. And actually, we got good results, and this accepted in the Life Science journal. Also, we try to see the effect of femtosecond laser with some cancer cell, breast cancer cell, T47. And also we could do a comprehensive study, which change all the parameters of laser like wavelengths, power, exposure time to reach the optimum parameter. And as I said, the goal of this one to have small laser device that could be used in clinically. This brief some of the research direction, but I can discuss in details any one of them if someone of you would like to know more details. Now I go to the second part. I will give a little bit detail about one of this research activity called nonlinear optics research. Maybe most of you know the history of nonlinear optics start after the laser, and by Franken from University of Michigan, and he sent the ruby laser through quartz crystal, and he observed two wavelengths, the ruby wavelength and other wavelengths 3, 4, 7. The field of nonlinear optics starts from that time. And in the linear regime, the molecule or sample absorb photons and emit the same photons, but in the nonlinear, the molecule absorb a photon and emit another photons. So here, this is the atom, picture of the atom, hydrogen atom. If in the normal case, but if we expose to laser, start some effect, and this effect become larger when the laser intensity increase, and you can see here the polarizability increase nonlinearly as laser field increase. There is a very common nonlinear optics process, second harmonic, and the first and second harmonic. So second harmonic, two identical same photon absorbed, and one new photon has frequency double the absorbed photon to omega emitted, and some frequency generation we have two different photons absorbed by material, and the sum of this two photon emitted new photon. And if there are different frequency, the material absorb one photon and emit two different photons. And the fourth process, third harmonic generation, the material absorb three identical photons, same frequency, and emit new photons have 3 times the absorbed frequency. We have, for example, in laser, so this nonlinear optics field used for developing mainly lasers. So we have inside the ZAG lasers that we have at Lira, we have the main light emitted from the ZAG medium 1064, and we use second harmonic to generate like KDB crystal to generate 532 green, and third harmonic to generate 350 nanometer. Also, the lasers that we have in Inspire, as I said, it's mainly based on nonlinear optics crystal. So we could, with using this laser, we could expand the MITI wavelengths from 600 to go to UV 345 and reach the mid-infrared just by using nonlinear optics medium. And also we have BPO crystal. We use it to reach to do third harmonic generation. So here, simple picture. We have medium. So we the nonlinear medium absorb photons, and we emit a different photon called idler, and also could also make amplification for the main input photons, input light. So we do this in the laser. We could make new wavelengths, generate new wavelengths, and at the same time we could do amplification. This can be is in the laser system, done in the laser system. They are not all the material could be classified as nonlinear optics material. There are parameters that could say this material could be used in this application, like nonlinear optical process, second harmonic, third harmonic. So we have some nonlinear refractive index. We have nonlinear absorption coefficient, and we have nonlinear susceptibility. And we could usually we characterize the material using N, nonlinear refractive index N2, and nonlinear absorption coefficient. We can get from N2 and beta. We can get the nonlinear susceptibility. So at LIRA we try to study the nonlinear material. In order to experimentally, in order to do this, there are different techniques well known to measure this nonlinear optical parameters, and they are very common for technique. But actually, as you can see, this all of this technique have a lot of optics and take some time for alignment and complicated. So there is another approach. They call Z-scan technique. This is developed by Mansour Bahi from University of New Mexico, USA. He developed this technique in 1989, and this is a very simple technique. We use just one laser beam, and have a lot of benefits. It is single beam technique, sensitive, setup is simple, and we can do the measurements in a very short time, and it can be used for study different the nonlinear optical properties of different material like solid, liquid, and gas. And we can see here this technique is used in many publications since the development till 2000 till current year. This scan technique, we have two approach. We have something called closed aperture and open aperture. In closed aperture, we focus the laser on the sample. Here is the sample, and we move the sample in the Z direction, and we record the transmission. Here close because we just monitor the central part of the beam. And from this, from measuring the transmission, we could determine the nonlinear refractive index. And the other approach is called the open aperture. We record this transmission as a function of the position of the sample along the Z directions. And from this measurements, we could estimate the nonlinear absorption coefficient. And as I said, from both of them, we can get the nonlinear susceptibility of the sample. For a nonlinear refractive index, the material could be a positive nonlinear refractive index. If we move the sample in this direction, we have got this transmission spectrum. We have can find peak, valley, and peak. So if we have such structure, we characterize the material like a positive nonlinear refractive index material. Negative nonlinear refractive index, the transmission different start. We have peak and valley. And how we get the nonlinear refractive index N2 from this curve? We have delta T is difference between peak and valley, and from this one we would phase shift. And from the phase shift, we can have the nonlinear refractive index. For the nonlinear absorption coefficient, the material could be reverse saturable or saturable. And this depends on if we have transmission curve like this one. So the material characterized as saturable absorber. And here you can see the absorption transmission increase. This means absorption decrease with increasing the intensity as we move the sample through along the z direction. And we have reverse saturable absorption if we have transmission curve like this one. So here we can see the absorption, the absorption increase with input intensity. How we get the nonlinear absorption coefficient? We have this transmission curve, and we get delta T from this one, from the base, difference between the base and the peak, or difference between the base and the valley. And we have beta can be obtained from this simple equation. And from beta also we can get the absorption cross-section, 2 photon or 3 photon absorption cross-section depends on the material. So we, in this direction, we focus on studying different materials like transparent or conducting oxide. That this material have a lot of applications like transparent conducting oxide, transition metal oxide, polymer, nano-sized material, organic and non-organic compound. So some example of this, quick example. So we have a setup for doing this nonlinear optical properties measurements. So we have two lasers, MITI and Inspire together, and we have the laser beam, and we have the sample here and sample on translation stage, so we can move it along the Z direction where the focus position change. And we could record here, we call this open power meter 2 or detector 2, but measures the transformation. We call this open aperture, where we could measure or estimate the nonlinear absorption coefficient. And we have the transformation through this iris. BM1 could measure the transformation, and we could determine the nonlinear refractive index. So we did this with some sample. We did this like copper oxide. It was like thin film and have 62 nanometer thickness. And we did before this, usually we did the linear optical studies and linear optical properties, so we could know the morphology of the thin film, and from the transmission, linear transmission, we could obtain energy gap, and from the energy gap we can know exactly how many photons absorbed in the sample. So here is the open aperture Z-scan results, and we fix here the peak power, laser peak power, 1.2 10 to 5 watt. And we can see here we change the wavelength 740, 80, 820, and this keep the intensity at 28 gigawatt per square centimeter. And here we get beta. So we change the wavelength from 740 to around 840. So there is a nonlinear absorption coefficient for each wavelength. Then we change the peak power, and also did the same study. We get also different beta. So we can see here we could tune the nonlinear optical parameters by tuning the laser wavelengths. And we did close aperture Z-scan to get information about the nonlinear refractive index. And here we have this regular structure for closed aperture Z-scan. And here we keep also the big bar, 1.8, 10 to 5 watt. And we change also the wavelengths. Here we can see the nonlinear refractive index as a function of the wavelengths. Then we have, from this result, we could summarize all of this graphs in one here. So we can here have the nonlinear absorption coefficient as a function of the excitation wavelength. You can see here for CuO, copper oxide, we have beta decrease with increasing the wavelength, and with increasing the peak power, the nonlinear absorption coefficient increase, but still beta decrease with the wavelength. And here this is the nonlinear refractive index as a function of the wavelength decreasing with increasing the excitation wavelength. We did also check the possibility of using such thin film as optical emitter. We can see here the output power as a function of the input power. We change the wavelength, so we can see some optical emitter characteristic for this thin film. We published this work in Journal of Optical Sensors America B. Also, we study zinc oxide doped with cobalt, and the thin film was 130 nanometer. Excitation keeps the excitation wavelength 950, and here is the open aperture transmission curves. And from this one, we can have the nonlinear absorption as a function of the intensity at constant excitation wavelength, and the saturation intensity as a function of the intensity. We also investigate the closed aperture Z-scan to get the nonlinear reflective index of zinc oxide doped with cobalt. And we have the nonlinear refractive index as a function of excitation wavelength, excitation intensity. And here we check whether we can use the zinc oxide doped with cobalt as an optical emitter. So we check first zinc oxide without doping, and we can see the transmitted power increase as a function of incident power. So there is no limiter property here, but once we use cobalt doped with nickel oxide, we have optical emitter here. And we this one published also in Journal of Optical Sensors America B. We also try zinc oxide itself, zinc oxide itself, but different thickness, 140 nanometer. We change the wavelength like 750 nanometer. And this is normalized transmittance and open aperture measurements. You can see this peak, so we call it saturable absorber. And we dope the zinc oxide with nickel, and thickness different. And we keep the excitation wavelength. Then we have different behavior. So we have saturable and saturable behavior and reverse saturable behavior mix. So two of them together in the doped thin film. We also did the closed aperture to get the nonlinear refractive index. We did zinc oxide itself and zinc oxide doped with nickel to see the effect from doping using nickel. And here is summarize all the results, how is the beta change with changing material like zinc oxide alone. So the beta change from minus 3.4 to 10 to 17. And when we dope this with cobalt, the beta change, and also we can see here in how in a change with changing the sample, I mean zinc oxide and zinc oxide doped with cobalt and nickel. And this we submit this work to Optical Sensors of America. Applied optics belongs to Optical Sensors of America, and also we tried transparent conducting oxide like TCO. We study ITO, thin film, and in this study we try to see the effect from different thickness. So here the open aperture measurements. And from this open aperture measurement, we get the nonlinear absorption coefficient. as a function of the excitation bar. We can see here decreasing with the excitation bar, and here we can did this with different excitation wavelengths. So also we try to see the effect from thickness. So we did the open aperture scan. This scan for ITO with thickness 170 nanometer to 80 nanometer, 380, and you can see different effects. This is small. Transmission is small. This means absorption is high. In transmission, absorption getting higher. So here different structure. We have saturable and reverse saturable together. Once we increase thickness, so there is effect from the thickness. We submit this to applied physics A. Also, we study some liquid, which also have some application like rhodamine 6G, which is a medium, active medium for laser. So we did also the open aperture Z-scan. Here is transmission curves at different wavelengths. We change the wavelength 700 nanometer, 7 till 850. And we change, as you can see, we change the excitation power here, 1.2, 1.6. So we have this summarize the results. This is the nonlinear absorption coefficient as a function of the wavelengths. We can see here is increasing with increasing the wavelengths at different excitation power. And here we could get from nonlinear absorption coefficient when have the absorption cross-section. Here the absorption cross-section is a function of length, and the two-photon absorption cross-section is a function of the also we have measured the nonlinear absorption as a function of the concentration. Here we're increasing the concentration, the nonlinear absorption increase. Also, we did close aperture measurements and at different rhodamine concentrations, and we use the nonlinear refractive index as a function of the mean 6G concentrations. We try to check whether we can use this as an optical limiter. We can different concentrations. You can see here it shows some limiter characteristic at higher concentrations, and we publish this work in the Journal of Molecular Liquid. Trying to study the colloidal silver nanoparticle, like silver nanoparticle. So we made using laser ablation nanoparticle in liquid, and we get sample from this liquid. We characterize this one with the size and shape. Then and we take this sample to do investigate nonlinear optical properties. And first we measure, we do TEM to know the size. So we have different sample, one average size 12 nanometer, and the other one 7.5 nanometer. We have 10 nanometer. So we with changing, this is energy fluence. We change the energy fluence, so the size of the nanoparticle change. And we take this sample and we do nonlinear optical measurements like open aperture here. So this is the first sample where we have 9 to 4 joule per square centimeter, this energy fluence. So the size of nanoparticle here will about 12 nanometer, here like 10 nanometer. And here is the smallest one, around 7 nanometers. So one can see here the absorption getting higher with a small size. And here we, this is, sorry, this is alpha, this is same like beta. This is nonlinear absorption coefficient as a function of laser power. You can see here the nonlinear absorption coefficient decrease with increasing the excitation power. And we did close aperture measurements, and from this one we have a nonlinear refractive index as a function of excitation power. We can see the nonlinear refractive index decrease with excitation power for different samples. And here summarize the nonlinear absorption coefficient and nonlinear factor as a function of the size. So we can see the effect from nanoparticle size on the nonlinear effective index and on the nonlinear absorption coefficient. And we tried also to study the optical limiting of silver nanoparticle colloid at 780 nanometers. So we can see also it has some limiter property. We published this work in Physica B. And we did also similar measurements of golden nanoparticle, colloid golden nanoparticle, and we submit this to Nanophotonics. And we also did for zinc oxide, we submitted optics express. This just for nonlinear as study, but we use this sample also to for biological application like antimicrobial, antibacterial applications. So by the end, I will conclude. I hope I was not boring, but I conclude here. I give you some brief about laser facility LIRA at Benedictine University, and I wish you to visit. All of you are welcome. And I did some quick overview about the ongoing nonlinear optical research at LIRA. We could tune the nonlinear optical properties by tuning the excitation laser, femtosecond laser. So we use benefits of this femtosecond, so we could tune the excitation wavelengths, and subsequently we could tune the nonlinear refractive index and nonlinear absorption coefficient. We are trying now to do metal alloy nanoparticle, and we also try to control the laser parameter to reach quantum dot size lower than 10 nanometer. And also we are going to use this one to check the nonlinear optical properties to see what could be obtained from such a small size and from metal alloy nanoparticle. By the end, I would like to thank you for attention, for your kind invitation. And again, I would like to thank Professor Harris, and I would like to thank the organizer. It's a very nice and successful conference. So thank you.
All right. Thank you very much. Thank you very much, Prof. Tariq, for your very informative presentation. You did very good work. So for that, I want to open maybe one question from the audience to ask.
Okay.
Is there any question from the audience? Look like don't have question. So if there is no questions, I think that's all. Thank you. We thanks Prof. Tariq Muhammad for his time and presentation.
Yes,
hope to see you again in the
yes.
next meeting or
Yes.
next conference.
Yes, thank you.
So thank you, Prof.
Okay, thank you.
So for the next sessions, we will have a technical presentation. Technical presentation from Dr. Muhammad Amirullah Sahuddin from his team. It's from Department of Chemistry, Faculty of Science, Universiti Malaya.
Yes.
So Dr. Amirullah, you ready?
Yeah, I try to share my screen first.
Okay. So you can start.
Okay.
The floor is now yours.
Okay, can you see my slide?
Yes, yes.
Wait. Second slide, can you see? Right? Is it changing? Second slide?
Not yet.
Huh? Not yet.
Not in a full screen.
Oh, okay. Wait. Sometimes got problem. I try to share entire screen lah. show entire screen.
Yes, now.
Okay, all right. So, Bismillahirrahmanirrahim, Assalamualaikum, and good afternoon to everyone. Thank you to the chairperson. I'm Dr. Amirullah Sahudin from the Department of Chemistry, Faculty of Science, Universiti Malaya. Together with me with the co-researcher Muhammad Suko Lilintan and Nurul Huda Abdul Karim from Universiti Kebangsaan Malaysia. So first and foremost, thank you to the organizing committee for the opportunity for this conference, Innovative on Optical Sensors. So my research interests on development of chemical sensors and biosensors, optical sensor and electrochemical sensor based on metal complexes. Okay, metal complexes for various applications, including food safety area. So today I'll be presenting about zinc 2 complex TiO2 chemosensor for visual detection of histamine. Okay, hope you enjoy. So histamine, what is histamine? Histamine is one of the biogenic amines occurring in protein food. For instance, the chicken meat, poultry, fish, okay, say beef, and any protein food, including the dairy products, cheese, and milk. So this histamine mainly formed by bacterial enzymatic reaction of amino acids during the storage or processing food. Other than histamine, there are a lot of biogenic amines related. For instance, tryptamine, tyramine, phenylethylamine, putrescine, and cadabrin. Okay, but the most widely studied is the histamine one. Okay, and it is said to be an important biomarker in determining the quality of food freshness in the food industry. But sometimes when we see the food packaging, we cannot justify the quality or the freshness of the food by looking at the appearance, the physical appearance. For instance, the chicken meat is still pinkish and it's still in the expiry date, within the expiry date. But however, we cannot justify the quality by its appearance. So we need to justify it, quantify based on the markers, based on the food spoilage markers, which is histamine. So histamine is one of the indicator of food spoilage or food freshness. So currently, there are a few conventional methods that are still employing to determine, to detect the histamine or other biogenic amines. For instance, the GC, gas chromatography, high performance liquid chromatography, HPLC, and capillary electrophoresis. However, these instruments require skilled personnel and could only be conducted in laboratory. And therefore, we as researchers need a rapid, cheap, selective, sensitive, and simple technique, analytical tool to detect this histamine. Okay. So previously, there are a few sensing material based on metal complexes, metal and a ligand. So for instance, here on the left side here is a copper-2 calcium complex by Nemio et al. 2019. It has been synthesized and said to be a good binder to the histamine. It's a fluorescent sensor for the histamine detection. Other than that, there is another candidate by Go et al. 2010, which is zinc 2 tetraphenylporphyrin complex. It shows a good binding towards the histamine with a good binding constant value, which is 8.74 to the power of 5. So the binding constant here shows the binding strength between the sensing material or the metal complex towards the target of an allied histamine. So the higher the Kb, the higher the binding constant, so meaning it's a good sensing material it is. Okay, so in this work, we propose a new sensing material based on zinc 2 hydroxyl functionalized sulfate metal complex. So there's a zinc metal center here. So why zinc? Because it is non-toxic. Okay, surrounded is a ligand of sulfane ligand. Sulfane ligand, a lot of aromatic ring here, and also we install one electron withdrawing group, which is the carboxyl group here. So the reason to install this kind of EWG group is to decrease the electron density in the sulfane ligand. Okay, we decrease the electron density here while enhancing the binding event between the complex and our target, which is histamine. Okay, another thing is the addition of the hydroxypropoxy side chain here. okay, hydroxyl solution, is to increase the solubility of the complex in water, because after this compound is synthesized, is produced, and we confirm the structures, we have to evaluate this sensing material, this complex, towards our target in a in a solution phase, meaning a binding solution study, before we develop this sensing material in a solid state sensor. And therefore, we need the solubility in water properties to enhance the binding event between the sensing material and the target of analyte. So here is the proposed binding mechanism. So here the complex 2, and here is the histamine. So zinc here is now 4 coordinated with the ligand, nitrogen and oxygen ligand here. So the binding event that we propose is zinc will provide another empty d orbital, okay? Suppose it theoretically is 5 coordinated, okay? 5 coordinated square pyramidal, but here is the 4 coordinated, it's a square planar. So there's another empty orbital, okay, to be filled by electron pair by our target. So here is the binding event, binding through a covalent, dative covalent bond. It's a coordination bond. Okay, it's a 1-1 coordination. Okay, so the objective here is to synthesize and characterize the hydroxyfunctional complex, and we will evaluate the binding strength between the metal complex and histamine using UV visible titration technique. This is a solution studies, and therefore we develop a solid state histamine fluorescence sensor using a fluorescence spectroscopy based on the sensing material. So the first, we synthesize the complex. Okay, here is our desired compound, which is complex 2. Before that, the journey is we have to synthesize the complex 1 first. So using the phenylenediamine and the aldehyde, and we produce the shift-based complex. So we send to the characterization, NMR, FDR, mass spec, and UV to confirm the structures. It took around 3 hours to get this product, very good amount, 80%, and then this complex were subjected to another addition of side chain here, the hydroxy proposed side chain, for about 3 days. Okay, with the presence of the chloropropanol and this potassium carbonate, and we got the complex 2 with a quite good yield, 50% in the brown precipitate. So this is our desired sensing material. So both complexes were characterized, will confirm the structures using the normal spectroscopy technique, NMR, FTIR, and ESI mass spec to confirm the weight, the molecular weight of these complexes. Same goes to the complex 2, NMR, FTIR, ESI mass. So after this complex have been confirmed, so we can the buffer, PBS buffer. So what we do is in the cuvette, in the UV visible cuvette, we just titrate 1 microliter of our target histamine, 1 microliter in the complex solution until at the beginning the absorbance is higher, so until it becomes constant. Okay, so there is a hyperchromicity of the absorbance, meaning that there's a binding event between the metal complexes and the histamine. So after that, we got this one, we analyze the spectra. So we replot, okay, we got the graph. So we calculate the KB. KB is a binding constant. How is the binding strength between our complex and the histamine? So we got around 3.67 plus minus 0.14 times to the power of 6. Okay, this shows that this complex shows a good optical sensing material, good binder towards the target. As previously, the literature reported is around 4 to 5 times to the power of 4 and 5, but in this project we got to the power of 6. Right after that, after we got the binding strength, so we subjected to the sensor development. So the sensor development is pretty simple. So we have the first sensor design must have the immobilization support. Okay, immobilization support or the matrix that hold the sensing material. So we choose the TiO2, titanium dioxide nanoparticles, the nano TiO2. We spin coat onto the soda lime glass, the normal normal glass, as a substrate. So the TiO2 is chosen due to its non-toxicity. It is provide large surface area, so it has a porosity there. So the porosity will be filled by our target, by our solvent complex. So next, we will spin coat our sensing material, and it is readily be used as the best sensor to detect the histamine. Okay, so we just dip our best sensor, the electrode, into the histamine solution. So the first thing, we have to undergo initial response studies. We are using the fluorescence spectroscopy. We want to make sure, is there any response or the fluorescent response before and after we expose the histamine in a solid state device, in a solid state sensor. Okay, as you can see here, the region A here, so we monitor at the emission wavelength around 370 nanometers. So before, this is a bare sensor electrode, there is just a bit of fluorescent intensity around 160 kind of. So after we dip into the histamine solution, there's a significant increase of the fluorescent intensity for about 50%. As you can see here, there's a glow here after we expose to the histamine solution. And therefore, there's a signal that this is a good response of the sensor. So we can go further to optimize and to do a performance studies of this sensor. So here are the parameters selected to optimize the sensor. The first one is we use the thickness of support, complex concentration, buffer type. There are a lot of buffer type, and buffer pH, at what pH the histamine works well, and also the reaction time of our sensor to bind, to sense, or to detect the histamine. So this is the optimized parameters that we obtained. So we will use all these parameters in the performance studies. This is very crucial. The parameter that we select for the performance study is the linear range. At what range it works? What is the limit of detection of our sensor can detect our target? So is it selective enough? The sensor can detect histamine, because there are various of chemical components in the food products, right? In the chicken meat, there are various histamine, tryptamine, amine, or other amines. So we want to make sure our sensor is selective enough to our target of analyte, which is histamine, and also reproducibility. Is it the sensor can reproducible results with a different of sensor piece of glass? Also, regeneration, how many times that our sensor can be reused? Is it disposable? Is it 2 times? Is it can be regenerated for about 7 times? These are very crucial parameters in sensor development. And the most important is the shelf life of the sensor. So what we got here is the performance value. The LOD is -10, it is histamine, RSD around this area, and the shelf life is 60 days. So here's the linear range. Okay, we run about 14 concentration difference. So the working range of the sensor is between -5 until -9 here. So we replot again to get the LOD. So the LOD that we obtain is 2.53 to the power of -10 molar, which is quite good as compared to other literature reported. Okay, so another the selectivity. So we tested on other types of amine, cadaverine, putrescine, primary amine, secondary amine, and tertiary amine. So histamine shows a good response because this sensor has been fully optimized, and therefore it shows a good selectivity toward histamine as compared to other amines. And the reproducibility is a reproducible results. Okay, we tested, it shows a good RSD. Around 400 intensity. But this sensor can be regenerated only twice, because after 2 regeneration cycle, it drops the force intensity, meaning that it's just a disposable sensor lah. Just like other sensor or other kits, for instance, the pregnancy test or COVID test can only be used once, disposable one lah. And how about the shelf life? Okay, the shelf life of the sensor, it retains its force intensity for about 60 days. If we market this sensor, so it is can be lasting about 60 days, or after 60 days, the fluorescent intensity going down, decrease, and so on and so forth. So to make sure, to prove the applicability of our sensor, so we have to do a real sample analysis. We want to make sure our sensor is pretty sure it can detect the histamine in the food product. So we use a salmon. So here, with salmon blank, we use a first sample, second sample, and third sample. And also we use the deionized water as a control to make sure there is no interference. So we got a recovery around 91 to 97%. We can recover back the histamine in the salmon sample. We spike the histamine in the sample, and we got a good recovery, good precision, and accuracy. So in a nutshell, this new hydroxyl functional complex has been synthesized and shows a good high affinity towards histamine with a good value binding constant in the magnitude of power of 6, while the developed local shift-based sensor exhibited promising analytical performance, which has been well validated with conventional HPLC in salmon filler samples, and hopefully this sensor can be used in the food industry for controlling the food quality and food freshness as a surveillance tool and analytical tool. Okay, thank you to Universiti Malaya for the facilities, and thank you for the UKM as well. It's a good collaboration with the funding GUP, and thank you to the Higher Learning Ministry, KPT, for the funding throughout this project. Thank you very much. If you would like to have a proper discussion or collaboration with me later regarding the sensor development, food safety area, and the complexes, please feel free to contact me via contact number here and also the email here, amirullah@em.emi. Thank you so much for listening.
Okay, thank you so much, Dr. Amirullah, for the presentation. So I'd like to open for question and answers if the audience have any questions.
I have 2 questions if you don't mind.
Yeah, sure.
First question is about the synthesis of your complex. The second synthesis resulted in 50% gain, was it?
Yeah, sure. Yeah, 50% only.
50% only. Do you know? Do you have any suspect as to where the losses are, and do you have plans on reducing the loss?
Well, actually, the final product is in liquid. So because the first step is we got the precipitate, so we can recover much more the precipitate powder. And the second step is the final. The product is in liquid, so we have to evaporate all the liquid using the rotovap, and therefore it yields around 50%. Maybe right after this we can. At current state, we have no idea on how to increase the yield for the second step because there's a lot of steps. We increase. We use a catalyst. We use a potassium carbonate, and other. If we increase the amount of the precursors, the yield is still lower. There's still a question for me. Thank you for the concern. Or if you have any.
Yeah, understood. Thank you very much.
Okay. The second question? Yeah, I thought you have 2 questions there.
Yeah, I forgot what was the second question. So sorry.
Okay.
I think.
You can contact me later. Yeah. Sure.
Yeah, I'll contact you.
Amirullah.
If I may ask a couple of quick questions, Dr. Amirullah.
Okay.
So what is the technology readiness level of the sensor? Would you say?
The technology level.
The readiness level, yeah, the readiness level of the sensor. Can it be commercialized already, or?
Oh yeah. The first thing, this one has been patented. So now, our team is collaborating with the AI department to develop a portable and regenerable sensor. We are looking for the grants to make it commercialized. But currently, just patented in Malaysia.
Okay, then you mentioned something about the shelf life. It was about 60 days, if I'm not mistaken.
Yeah, 60 days.
Yeah, 60 days. Is there any way to further lengthen the shelf life?
Sure, we can. We can change the immobilization support. So maybe we can change the TO2 using a polymer that is polymer, or we have to optimize on the immobilization.
But that would affect the performance, wouldn't it?
Need to yeah, it will affect the performance. So we have to try and error using other support or other matrices. So I'm thinking about using fiber optic as the support, and we coat the fiber optics using the chassis material. So still thinking the researchers to collaborate with.
Yeah. Okay, thank you very much.
Excuse me, yeah, Dr.
Yeah.
I remember the question just now. I wanted to ask, what was your you did your spin coating, right?
Yeah, spin coating.
Oh.
Yeah, spin coating. Yeah.
Yeah, what was your parameters, and what's the thickness?
The thickness.
How fast did you spin it?
2000 RPM for 20 seconds.
Okay, for 20 seconds.
The thickness is 0.3 micrometer. 0.3 micrometer. That is the best for the TiO2 to work.
Understood. Thank you.
Okay, sure.
Okay, if there's no more question, I would like to invite our next presenter, Faikah Abdul Latif.
Yes, hi. Sorry, I'm using account in the name of Teenage due to my Microsoft Teams account have some technical error.
Yeah, there will be no problem. I think the organizer can take note of that. Shaman?
Okay.
Okay.
Okay, hi. Hi and Assalamualaikum. My name is Faikah Nur binti Abdul Latif. I'm from Department of Electric and Electronic Engineering Faculty of Engineering Universiti Pertahanan Nasional of Malaysia or National Defence University of Malaysia. Okay, in this presentation, I will show you my progress on developing the optical fiber sensor in order to monitor the temperature of PV panel. This slide will cover from introduction of the project, my progress, including the experimental works and conclusion to be made. Okay, as we know, there are various types of renewable energy sources exist nowadays, such as wind, where some countries already made a wind farm, hydropower, geothermal, biomass, and solar. My study will focusing on solar, where solar is one of renewable energy that is widely used in overall countries, such as if you can see in my slide, top countries with solar power, where they got high demand of energy. They use renewable energy solar to generate electricity. Okay. And my focus is on making a temperature sensor by using optical fiber sensor, where if we say that we want to use solar power to generate energy, we must have the photovoltaic panel as a medium to catch the energy in order to produce electricity. Therefore, it is very important to take care of the performance of the photovoltaic panel itself. And temperature is one of effects that can give impact to the photovoltaic panel, where if too high temperature of the photovoltaic panel may result in decrease in cell efficiency about 0.5% per degree Celsius. Okay, when the PV panel were exposed to sunlight for such a long duration, the absorption of the solar radiation will be high. After that, the photovoltaic panel also will produce excessive heat and causes increase in temperature, which then will affect to power output and efficiency of PV panel itself. Okay, when the temperature of the PV panel is too high, it may lead to aging of the photovoltaic panel surface itself. There are various methods of thermal assessment on PV panel. Okay. One commonly ways in assessing the temperature of the surface of the photovoltaic panel is based on IoT based or by using the wireless sensor network. Because of both of, if you can see on my slide, both the IoT-based wireless sensor network and Pico software actually two common or more likely similar medium where then we need to utilize more sensors on the PV panel, and it also requires quite high cost in for the sensor probe itself and the system that we need to in order to generate the results. Okay. So my study is I will propose the integrated optical fiber by where the fabrication of the optical fiber is by modifying the part of optical fiber structure. Okay, let's look at the on the right of the slide. This the working. Okay, I would like to tell about since the previous two methods of thermal assessment is by using IoT and sensor probes. Okay, and so my a temperature sensor by using optical fiber. Okay, the working principle of optical fiber is the optical fiber will works with the principle of total internal reflection, where the light's traveling in the optical dense medium, where it will hit the boundary at a steep angle, which is larger than the critical angle for the boundary, which then will cause the total internal reflection. Okay, on the top right side is the basic total internal reflection, and on the below in the pink composed structure for my optical sensor, where it is actually just a simple combining of single mode fiber, no core fiber, and single mode fiber. In between of the combining join of the between single mode fiber and no core fiber, the reflection of the light will be disturbed and the propagation will not we call that like similar. Okay, that's I will discuss further where we see the results. I have two objectives for this study. First is to develop a sensitive temperature sensor by modifying the structure of the optical fiber for sensing the temperature on PV panel. And secondly is to investigate the performance of the optical fiber fabricated in terms of its sensing sensitivity. This is my project scope. The first one is to conduct a literature review on variance optical fiber sensor. Yes, it is optical fiber nowadays quite well known to use as a sensor where it because due to its structure and characteristic which is very sensitive towards disturbance. Therefore, if we have such a good result displays, then it can be it can be used as a sensor very well. And the second one is to provide an effective design of optical thermal sensor on PV panel. And lastly, to investigate the best sensing length of optical sensor to give the optimal result in thermal detecting. In this study, my variance parameter is on the length of the sensor. And let's go into the methodology. This is the overall flow diagram of the experimental progress. This work comprises of two main phases, where the first phase is just a simple fabrication process where involving the cleaving and splicing. However, the cleaving and splicing process must be done properly in order to get the best results, while we splice the two type of fibers, there's no much losses, because too much losses will lead to not a very good result at the end. Okay, and the second part is to test the optical sensor on PV panel. If you can see on below, I will placing the sensor on the PV panel and recording the temperature by using that data acquisition and collecting data which will generate on post. Okay, this is the overall scenery of the during the experimental works. Okay, the halogen, if you can see the halogen light will act as the sun in actual life. And there's a dimmer over there where I will control the knob from starting from a very low light, then until the very high that it can goes, while the temperature of the photovoltaic panel itself will be recorded parallel measure in parallel with the while the PV panel receive lights, and the temperature measure parallelly by using the AQ. If you can see in the previous slide, recording the temperature using the AQ. Okay, and on the right side of the slide, if you can see, there is how I put the sensor on the PV panel. I have to use the special tapes which suitable to be put on the PV panel that will not disturb other effects. I don't want any other external effects on the sensors. Okay, so the optical fiber structure is placed on top of the PV panel to detect temperature changes of the PV panel. And the type K thermocouples. Thermocouples is the white and green color one, which attach very near to the optical fiber to measure the temperature at certain location, at that location lah. And then the thermocouple is then connected to the AQ to monitor the temperature. And then the result will then show on the optical spectrum analyzer and to be analyzed later. Okay, this is I would like this result is actually I want to tell the both sides of the, if you can see, the photovoltaic panel is actually have both sides. On the surface, on the rear and on the back side. Okay. So this graph shows that both sides of the panel actually also experience increment in temperature. Okay, therefore, it is important for us to monitor the temperature of the photovoltaic panel and the monitor the temperature of the photovoltaic panel so that it does not go very high that will damage the photovoltaic cell. Okay, this is the early results that I gained. This one is for a sensor at 1.5 cm. Okay, you can see the shift length. There's a shift length. Or not. That is the overall patterns of the wavelength created. Okay, and on the right below is the result that I gained at this early stage, where it shows that it shows linear increasing. Okay, increasing of wavelength spotted, wavelength peak spotted. Okay, which means that my optical thermal sensor quite sensitive at the temperature of between 40 and 50 degrees Celsius. This is for 1.5. Okay, and this one is for 3.5 cm sensor. We can observe here that there's shiftment of wavelength different from the 1.5 cm sensor. It may be because of the longer the sensor that I fabricate, the more disturbance that we give to the structure itself. Therefore, the more disturbance will give more vigorous total internal reflection that results in variance pattern of wavelengths. Okay. However, for this 3.5 cm sensor, the patterns of result is linearly decreasing, and this sensor is actually still in working progress for the next length, and also maybe I will repeat for this 3.5 cm sensor. Okay. In conclusion, that can be met at this stage, the longer the no-core fiber, the more interference pattern be created, and the sensor more sensitive at temperature of 40 to 50 degrees Celsius. And the sensitivity can be measured from the slope of the graph as shown before. Then to measure sensor able, and the last one is to make sure the sensor able to measure up to 60 degrees Celsius in future works. Because as for now, I only can get the best results between 40 to 50 degrees Celsius. Friends? Okay, thank you.
Okay, thank you very much, Faika, for the presentation. Is there any question from the audience? I have a few questions, Faika, sorry.
Okay.
What is the insertion loss of your sensor? Because you splice a single mode fibers with no core fiber. So actually the guide cannot be guided because there's no core in the no core fiber. So what's the loss of the insertion loss of the device? I mean of your sensor.
Okay, thank you for the question. Okay, actually, since this is such a very simple simple, what you call that, simple procedure. So I not yet get the actual losses that occur at the certain area lah, because when I splicing both of the structure, on the splicer it shows only 0 dBm, which
yeah, the splicer always shows 0
yes,
dB, but
0
in
dB.
actual case the loss would be
So
be
yes,
different.
actually should be have losses that losses should be can be measured lah. Maybe in the next session I will find on that. Thank you.
Yeah, and have you ever tried? I mean, for example, now you just splicing the no-core fiber with the single mode fiber, so you get a certain sensitivity in detecting the temperature. But have you ever considered, I mean, coating, if you were to coat the no-core fiber with a material that is sensitive to temperature, for example, and then would it be able to increase the sensitivity of the sensor? Have you ever considered that? It's just an idea. I don't know whether, because I'm not a chemist, but I don't know whether a material can improve the sensitivity of the sensor. So maybe you can look into that as well.
Yes. Yes, I think I might consider about that. For example, like the maybe phase change material. Yes, maybe I will study further on that, because that is also one of my literature review. It is just that as for now, the first stage is to fabricate, just combining the structure. But thank you for the idea.
Okay, and my last question would be on your graph, on your optical spectrum graph. When you mentioned the wavelength, is it this? How do you define the wavelength? Because it's actually a broad spectrum.
Okay. That one I just use the I get the data from OSA. From OSA, then I take it and transfer to the Excel, and then from the Excel I put formula to pick only the maximum or minimum value. So from there I plot the graph.
So it's actually the peak wavelength lah, you would say. I mean the wavelength with the highest intensity.
Yes, but actually if you can see my 3.5 cm sensor, it also have that deep value. That one I'm not yet analyzed on that. Maybe later I will analyze on that also lah. But I only use the Excel to take the value lah.
All right, thank you very much for your presentation and for your answers.
Okay, thank you also for the idea. It's such a good idea from chemists. Okay.
Okay, thank you. Sorry, my apologies. I would like to invite the next speaker, Muhammad Ashraf.
Okay, let me share my screen, Doctor. Can you see my screen?
Yeah, we can.
Okay.
You have to enlarge the.
Yeah. Is my voice clear?
It's quite clear.
Okay, thank you. Okay, so I can start now, right?
Yes, please do.
Okay, good evening, everyone. So today I will be presenting ground displacement measurement using a fiber Bragg grating based extensometer system. So the contents of my presentation would be the first one, introduction. Second one, I would go briefly on landslides and ground movements. The third one is my design. The fourth one would be my setup, followed by the results and the publication. Okay, we go for the first one. Okay, as for the introduction, prior to any landslide, the soil structure will change as it loses its cohesion, causing ground movements to occur. It is highly important to monitor such events in order to develop an early warning system for landslide monitoring. Therefore, an optical-based extensometer system was developed based on fiber Bragg ratings. Okay. So, these are the landslides that had occurred over the past 2 years. This picture here is actually the ones that happened in Mumbai last year on July. If you can see, it is quite catastrophic, in which at least 30 people are dead. And this one is actually happened in Malaysia, in Ampang this year, March 2022, in which 4 are found dead. Therefore, these landslides are said to be a catastrophic event, and people might have lost a lot of things due to that event. So how do we solve this issue? We can monitor the ground movements to form an early warning system, also known as EWS. As you can see here, this is actually an electrical-based extensometer in which it has a readout cable. Then, so by using devices such as the device that I had presented just now, the extensometer, this will have the potential to prevent a lot of deaths and economic losses. However, the conventional devices have some limitations in which it is expensive, cannot be transmitted over long distances, it is prone towards lightning strike, and because it is electrical and electronic based, so it might have some short circuit problems. It is not immune towards EMI, electromagnetic interferences, and large scale scope monitoring cannot be achieved. Therefore, to overcome such limitations, we propose an optical-based extensometer. Optical-based devices have some key advantages, which is the key ones are like it is low cost, it can perform large-scale slope monitoring, it can perform remote long-distance monitoring, ease of installation, it is also immune towards EMI, and it gives a high-speed response. So, moving on to the design and principles. Because optical sensors, there are a variety of optical sensors available, we had chosen fiber Bragg gratings as the main sensing element of our device due to its advantages, in which it is not influenced by EMI, it is free from any electrical or electronic problems, it acts as an accurate point sensor, and over 100 sensors can be connected just in a single line of optical fiber, and it is also cost effective. This is the principles of fiber Bragg gratings, in which this is the incident light. Whenever an incident broad spectrum of light propagates through the gratings, a specific wavelength is reflected back, while the rest of the spectrum is transmitted and unaffected. This is the equation of FBG, in which it is based on wavelength shifts. You can see here, FBG is affected by both the change of strain and change of temperature. So it is affected by both. What I meant by that is, let's say this is the reflected spectrum that we got from here, this one. So whenever there exists any strain or temperature changes, the Bragg wavelength would shift at this amount, at this periodic amount, causing the Bragg wavelength to shift, and then from the wavelength shift, we can translate it into any kind of information such as displacements, in which in this presentation I would discuss about ground movements, right? So that is why I would translate the information that I got from the Bragg wavelength shifts here into ground displacement. And then for my extensometer design, it comprises of this strain sensor. I had fabricated this sensor using a 3D printer in which the dimensions can be seen here. The fiber containing the FBGs are inserted inside a hole, and it is glued together using a cyanoacrylate glue, also known as super glue. This is actually the real picture of the fabricated sensor that I've done. And then I had used thermoplastic polyurethane material to embed the fibers and FBG. So thermoplastic polyurethane is actually good because it has high flexibility, good strength and sensitivity towards strain changes. And then here a thin brim is included in the design to allow better bed adhesion on any surfaces. This one here is called the brim. Okay. So the material that I've used is thermoplastic polyurethane. Its niche markets are automotive industry, in which it has been used in tires, sports and leisure, in your shoe, and tubes and hoses. And these are some of its key properties. It has good flexibility over wide temperature range, robust weather and UV resistance, excellent tensile strength. Okay, moving on. This is the 3D printing process of strain sensor, in which you have to first design the sensor using any design software that you are comfortable with, such as Fusion 360 or SketchUp. For me, I prefer using Fusion because of its features. And then from here, you will generate an STL code in which it will be uploaded into a 3D printing software, for example, Cura or Prusa Slicer, depending on which 3D printer that you are using. And then from this 3D printing software, you can further edit and generate a G code as an end product. What I meant by further edit is sometimes, let's say if I'm using the thermoplastic polyurethane material, the printing temperature and the printing speed is different than other temperatures. So that is why we would need to further edit and generate a G code as the end product of the software. And then we would start printing of the sensor body. Then you would just have to wait for a few minutes. For this design, it took me about 5 minutes to print. So it's kind of quick actually. Okay, and then for temperature compensation. As you can see here, this is basically a 2D sketch of my extensometer design, in which 5 strain-sensitive FBGs are used and placed at one side of the PVC pipe, and then one FBGT is placed inside the pipe here, and it acts as a temperature sensor. The reason I place FBGT inside here is because, like I have told everyone just now, since FBG is affected by both strain and temperature, the Bragg wavelength shift would be affected by both parameters. So FBG1 till FBG5 would be affected by both temperature and strain, while FBGT, since it is placed loosely inside the pipe, it will only be sensitive towards temperature, no strain changes will affect FBGT in this case. This is the basically the schematic of the design here. This is FBGT joint. This is its cap. Okay. So for the extensometer design, as you can see in the you have seen this diagram just now. This is actually before the ground moves, which 5 FBGs acts as a strain-sensitive FBG. Then FBGT here is placed inside the pipe, acts as a temperature sensor. The function of the temperature sensor here, FBGT, is to correct any temperature effects that occur inside the system. And then after ground moves, you can see that this part here, FBG3, part of the pipe, FBG3 happens to be, if you can see here, FBG3, the section of the pipe where FBG3 are placed is bent more compared to the section of the pipe where FBG2, FBG4, and FBG1, FBG5 are placed. So FBG3 will have the biggest wavelength shift compared to FBG2 and FBG4, and also compared to FBG1 and FBG5. So FBG1 and FBG5 are placed on the PVC pipe towards the ground movement direction here. So like I said just now, due to the change in length of the pipe, so the FBG would be able to measure strain and translate it into displacement. The strain, the wavelength shift of the strain sensitive FBG can be converted into displacement. Hence, after converting it into displacement, we can monitor how much the ground moves. And then this is basically an early development of my device, in which this is the fabricated sensor. And then I had protected the sensor with a self-fusing tape, a tape which has very good properties, and it will only stick to itself. That is why it is called self-fusing tape. And it is used as the protective tape due to its excellent moisture properties, a good operating temperature range, which is from -100 degrees to positive 100 degrees Celsius, and it has good flexibility, which would prove to be beneficial for my design. And then after I protect my FBG sensor using this protective tape, I would wrap a nylon cloth to wrap the extensometer body. The reason I use nylon cloth is to provide waterproofing and to protect the extensometer body during field testing. And then on the outermost layer, I had used a black plastic sheet to ensure a smooth installation and to conserve soil moisture during small-scale field testing. Okay, moving on. This is the setup for my test, in which I had tested in two environments. The first one is laboratory testing, and the second one is small-scale field testing. This is the setup for laboratory testing. Okay, as you can see here, this part and this part is fixed using a M6 Allen bolt, and then I displaced the center part by 2.5 cm intervals, in which and then I would measure the wavelength shift of each FBGs just to monitor the trend of the wavelength shift exhibited by all FBGs here. And then this is the small scale field testing. After testing my device in a laboratory environment, I had tested in a small scale field testing, in which I had used a lateritic soil. This is the common soil used here in Malaysia. This is the common soil here in Malaysia, and this is basically the setup. I had placed weights on top of each FBG locations. As you can see here, this blue indicator is not actually the FBG. The FBG is actually at the bottom side here. It is actually the FBG indicator on the opposite side of the FBG. So meaning all FBGs are on the bottom side. And then when we place the weight here, the pipe would be bent down, causing the gratings of the FBG to be stretched due to the pipe being bent down. So as we place this weight here, logically the weight, the force distribution would be focused more on this part. So most probably FBG5 won't measure any responses. But if we place this weight on top of FBG3 here, which is at the center of the pipe, it can be said that the wavelength shift the wavelength shift captured by FBG3 are more as compared to FBG2 and FBG4, because they are further from the bending point here. Okay, so basically this is, I had also 3D printed this using PLA material to hold the pipes inside the box. It is also tested in both dry and wet soil environment. Okay, moving on. This is the real pictures of the setup. This is the laboratory testing, in which the pipe is bent towards this side. And then this is the small scale field testing. And how do I know the location of each FBG upon burial? because when we bury the extensometer under the ground, it would be a difficulty for us to locate each FBG location. So that is why when I placed the extensometer here, I had first marked each FBG location using a cloth tape here. So when the pipe is buried, I can put the weights at the correct location so that a good response can be obtained. Okay, this is more pictures of the small scale field setup. Okay, and then I had also performed temperature characterization of the FBGs. This is to correct any temperature effects happening inside the system. It is placed inside water bath and it is heated over a temperature range of 27 to 50 degrees Celsius. So this is the laboratory calibration results that I have obtained. As you can see here, the response obtained by FBG3, because it is placed at the center of the pipe, and meaning it is at the bending point of the pipe, it will have the highest response of 0.036 nanometer per centimeters because it is positioned exactly at the bending point. This also shows that because it is at the bending point, the Bragg wavelength shift is the highest compared to the other FBGs. FBG2 and FBG4, their responses are more or less similar, and the same pattern can be seen in FBG1 and 5. Y0 here actually represents FBGT, in which FBGT does not have any response towards strain. So means that it can act as a reliable temperature sensor. And then I had tested the FBG sensors in a water bath at a temperature range of 25 degrees C to 50 degrees Celsius, and the obtained sensitivity is 18.5 picometers per degree C. Okay, this is an example of the extensometer's response based on FBG3. So if you can see here, this y-axis here is actually the whole extensometer length. So if you can imagine, like this part from this part is actually the pipe, and FBG1 is located at this this length along the pipe, along this 180 cm of pipe. So as you can see here, when the weight is applied on top of FBG3 in dry soil conditions, this is their response. This is all FBG's response towards strain. And if you can see here, FBG3 has the highest response because the weight is applied on top of FBG3, which is also the bending point of the pipe. That is why FBG3 has the biggest strain as compared to other FBGs. And then from the values that I have obtained here, I would do some mathematical calculations and would convert the values of strain into displacement, in which I have obtained that FBG3 is the displacement of FBG3 is the highest as compared to the other FBGs. I've also done the same thing in wet soil environment, in which I have placed about 1 kilogram of I think about 10 liters. It's 10 liters of water inside the box, and then what I have obtained is the strain captured by the response in terms of strain by the FBGs is higher than there is in dry soil. So it means that when you apply your device in a wet soil environment, the pipe will be bent more due to the wet soil properties, and this can also be converted into displacement, as we can see here. So if we apply weight on top of each FBG locations, the graph would look more or less like this. So if you can see here, this side is actually the dry soil, is the wet soil, dry soil and wet soil. So for FBG1, if the weight is being applied on top of FBG1, it can be seen that FBG4 and FBG5 have no responses. The FBG that obtain such response is only FBG1, 2 and 3. And then when we apply the weight on top of FBG2, we can see that the other FBG started to have responses as well, followed by FBG3, FBG4, and back to FBG5. Then the right side here would be the response when the FBGs are, when my extensometer is being placed inside a wet soil environment. So this research has actually been published in IEEE Sensors Journal with an impact factor of 3.301. It is being published on May 2022 actually. So I think that is all from me. If you have any questions, you are free to ask. Thank you.
Thank you, Ashraf.
Welcome.
So I open the Q&A session to the audience. Any question for the audience? Or you can ask in the chat box. I will read to Ashraf.
You can also email me if you want. Actually, I have left my email and my number in my last slide.
Okay. Okay. Anyone interested in his research or want to ask any question can directly email Mr. Ashraf. So I would like to proceed to the next session. My name is Siti Aisha. I will be a chairperson for this session. Without wasting any time, I would like to invite Nur Hidayah Mansur to present her technical presentation. Hidayah, you can start now. You can share your slide.
Hello, can you hear me?
Yes, yes, I can hear you.
Okay, wait. Gonna share my screen. Oh. So can you see my screen?
Yes, yes.
Okay, Assalamualaikum and a very good evening. I am Nur Hidayah from Universiti of Malaya. Wait, do I need to? I forgot to open the camera. Okay. So right now I'm doing a master by research at Photonics Research Centre, Universiti of Malaya under the supervision of Prof. Haris, Dr. Aisha and Dr. Zarif. So today I will be presenting about the Q-switch pulses in the erbium white-erbium dot fiber laser and its usage in the sensor application. So my main objective is to generate a pulse laser, mainly Q-switch and mod lock. But in this conference, I will focus more on Q switching using a double-clad erbium white-erbium dot fiber as a gain medium in the 1.5 micron region. So normally people will use erbium dot fiber in the C-band region. Normally people will use erbium dot fiber to generate laser in the C-band region. However, power scaling in the EDF is limited due to photo darkening and some bottlenecking effect. So until today, we have concluded that the most efficient method EYDF is to use EYDF, the gain medium, to achieve hundreds of watts optical output power in order to obtain a high power laser in the 1.5 region. So basically, this is the characteristic of the gain medium itself. Erbium white-erbium dot fiber is a very special fiber as it has a two rare doped material inside, which is erbium and white-erbium. The process actually, white-erbium will absorb the energy and pass to the erbium. So that's like a simple explanation, or you can read on the slide on the energy level diagram of the gain medium. So for my experimental setup, I will be using a pair of 915 laser diode. So this laser diode can maximize until 10 watts of output power. So right now we are just using like around 7 watt to avoid damage to laser diode from being overpumped. And then we coupled all the laser diode into a pump combiner to combine all the power. And then the output of the power combiner will be inserted into the gain medium. So it will be absorb the signal at 1.5 region. And then the output of the gain medium will go through the coupler. Is a 70-30 coupler. So 70% of the signal will be connected to the measuring equipment, which is the OSA, oscilloscope, spectrum, and others. Whereas the 30% of the signal will pass to the isolator to ensure a unidirection signal and pass to our SA. In this setup, if you remove the SA, we can get just a CW, continuous wave laser. But in order to get a pulse laser, we have to do an SA. SA is saturable absorber. In this research, I'm using a CDTE thin film, cadmium telluride thin film, saturable absorber to create a pulse laser Q switch. So for the results, we can see that optical spectrum in figure A, we have a center wavelength of 1534 nanometer and with a 3 dB bandwidth 2 nanometer. It's not too broad. And then the oscilloscope pulse train at 1.4 watt. We have found the frequency of 66.17 kilohertz. And the minimum pulse width that we got is 1.3. Oh, sorry, it's not a minimum pulse width. The initial pulse width we get is 1.3 micron. And then the RF spectrum is around 40 dB. And then we move on to the repetition rate and the pulse width. We know that the characteristic of the Q switch is that with increasing of pump power, we can get higher repetition rate but lower pulse width. So in this work, we have get the maximum repetition rate, which is 99.5 kilohertz, and the pulse width is 2 micron, the minimum pulse width. So for the graph of output power, we are pumping from 1.4 watt to 3 watts of output power. And we are pumping 1.4 watt until 3 watts of pump power, and then we get around 70 milliwatts power of Q switch. The maximum and pulse energy which we get is large, is 703 nanojoule. So the graph on the left, the A graph is the stability, which we tested the Q switch pulses for 1 hour, and we observed that we observe that there are no changes in the shape or no wavelength shift happen. And the graph on the B, the figure B, is just to show that with increasing pump power, the oscilloscope trace different. So with increasing pump power, the pulse width is become more narrower. And then we compare our work with other works. So the first four is the SA, saturable absorber, that we use is the one that we employ to the gain medium of EYDF, which is the same. And then we compare with our work that our SA that we use in the EDF also. So we notice that our work has the largest output power and maximum pulse energy with maximum repetition rate. This means that the double clad, the erbium dot fiber, erbium white dot fiber is actually we can use for, is quite promising for power scaling. And then because previously we can see that the output power of the Q switch in the EYDF is around like 5 to 1560 milliwatt, the highest output power, and our work has the highest output power of 70 milliwatt. So that's all. Thank you. You can contact me on the email below, dayas909@siswa.um.edu.my for free to ask any question.
Okay, thank you, Hidayah, for your presentation. So for the Q&A session, anyone want to ask questions to Miss Hidayah? Or you can type a question in the chat box. I think without wasting any time. I would like to invite Mr. Muhammad Shamil to present his technical presentation. Shamil, you can share your slideshow.
Okay, thank you, Teacher Aisha, for chairing the session. Okay, without wasting any time. Okay, Bismillahirrahmanirrahim. Assalamualaikum. A very pleasant evening to everyone. So I'm Muhammad Shamil. I will do a presentation regarding my work, which is a temperature-independent vibration sensor. It is a vibration sensor based on a Fabry-Perot interferometer using FBG approach. Okay. Then firstly, we go to the outline of my presentation. I will do some basic introduction regarding why we do this project, why we need to design such sensors for the real field applications, and then why we use FBG, fabrication of FBG, and then we moving on to the Fabry-Perot interferometer itself, how it is being manufactured or fabricated, and then how it is implemented into the FBG, and then we go directly to the temperature independent vibration sensor itself in terms of the design, experimental setup, and the experiment. Okay, firstly, the introduction. Mainly, the main motivation of this, what we call it, project is to address the landslide in Malaysia. How do we do a monitoring program for the landslides, which we know that is very crucial during these times. Okay, then you can see landslide in Malaysia. We focus in Malaysia. So this is a very recently, 26 November last year in Posiang Perak, the landslide damages the roads. And then 2 December in Blue Valley, Cameron, as we all know, the 2 cars trapped inside lived, 2 died during the catastrophe. And then 26 December, UIA Gombak, about 128 students were displaced because the landslide or the structural damage happened nearly at the hostel or the male dormitories. And then 10 March 2022, in Taman Permainan Bukit Ampang. So this one is at least 4 died. So this address why we need this landslide monitoring system or sensors. Or it's better if we do an early warning system. Okay, so that there are conventional sensors out there that is widely used by the civil engineers, but there is limitation. This one has been presented by numerous presenters before me, and then the limitation is expensive. The interferometer itself can cost us about 10,000 ringgit. Large scale monitoring cannot be achieved. And then short circuit, which is, we know, conventional based sensors use electrical system, and then EM interference. Okay, this one I'm going to skip because has been presented before. And then we go to the fabrication of FBG. In our lab, we fabricate our FBG. We fabricate the FBG ourselves by using the face mask. There are several methods on how to fabricate FBG, which is one is laser direct writing, and then this one face mask, and the other one using a prism to create interference pattern. The main idea is to create interference pattern at the fiber core. So in our lab, we do a face mask. We use a face mask, which is the face mask act as a filter. So when the excimer laser pass through the face mask, it will create interference pattern at the fiber core. So when the laser beam is incident, the beam is divided into several diffraction orders. Then the 2 orders start from the same point. And then at the nearer field, an interference pattern is produced as the 2 orders cross each other. So the figure as reference. And then after the process has been done, you can see the gratings, which is the interference pattern at the fiber core. And you can see at the right picture, see the broad spectrum, you see incidence spectrum coming into the fiber core, which is the gratings, typically about 5 to 8 millimeters. Then you can see some lights are reflected and some is transmitted through the fiber. Okay, the transmitted spectrum is just the broad spectrum without the reflected spectrum, and the reflected spectrum is based on this equation, which is the Bragg wavelength equals to 2 refractive index aperture, which is n effective is the effective refractive index, and the aperture is the grating period, which is the distance between the grating. As you can see here, this one, there is grating, so the distance between the grating is the aperture. So to use or to design an LBG sensor, you need to know the equation, which is the basic, this is a well-known equation, which is the Bragg wavelength equals to coefficient of strain plus coefficient of temperature, which is we need to know that LBG is directly affected by strain and temperature. Okay, then you can see here the initial Bragg wavelength with 2n aperture. So this is initial length, distance between the grating, and then when we strain the FBG, you can see the shift in the Bragg wavelength with a different refractive index and the different grating pitch, which is the grating distance. So this is how we calculate, means the wavelength shift we calculate into what we want to measure. For example, tilt sensors or vibration or pressure, something like that. Okay, this is the normal FBG interrogation setup, how we interrogate FBG. So you can see ASE is a broad spectrum. You can see from this one, it's a broad spectrum. It comes to optical circulator. We have a 3-port circulator. The port 1 will go into port 2 and port 2 will go into port 3. So in this case, the broad spectrum coming to port 1 goes to port 2, and port 2 will go to the FBG, which is your point sensors or anything sensor, any sensors that you are fabricating. So the reflected spectrum will come back into port 2 and go to port 3 where we place our OSA or integration setup that will go to the laptop. Okay, so the advantage of FBG, low cost, high speed response, image EM, and can be multiplexed. So for those who are not familiar, can be multiplexed means you can put several or as many sensors as you like within the same fiber. So for example, you have 10 kilometers of fibers and then you can place as many sensors as you want. That is can be multiplexed. Okay, then we go to Fabric Pro interferometer. So the basic is the Fabric Pro uses the phenomenon of multiple beam interference that arise when light shines through cavity bounded by 2 reflective parallel surface. So the key point is they have a 2 reflective parallel surface. So you can see from the diagram the incident light gray, and then they will come into a collimating lens, and then they will pass through mirrors. So these 2 mirrors that create the multiple beam interference. Okay, so then this is how we implement the interferometer into using FBG. So as you can see from the first diagram, you can see that there's 2 gratings within the same fiber core. So 2 gratings region. So you can see between the gratings, there is LFPI, which is the interferometric region that will cause, that is what we call the in-fiber interferometer, because the grating will act as a reflective panels for the light. Because from what I just said just now, the light will reflect back due to the grating. So when the light reflected by these 2 gratings region, so you create an interferometric region. So you can see at the bottom pictures, so that is FBG with 1 peak, that's normal FBG, and to the right is the comb-like spectrum is the FPI, which from that we can obtain from the first picture. It is the experiment setup. So this is a 980 nanometer laser diode. So the laser diode was pumped to a EDF, erbium doped fiber, through a WDM, wavelength division multiplexer, to produce a broad amplified spontaneous emission, a broad spectrum over the range of 1550. So this emission passed through the FBG, the first FBG, as you can see here. So which then emitted at port 2. It goes out to port 2 and it goes to the FBG FPI here. So this one, as you can see, this square box, this is where the sensing element, we call it the sensing element or the sensing mechanism. So in the design of FBG FPI, these 2 type of FBG, these 2 type of fiber must be placed closely together and have the same range of wavelength peak, as you can see on the right side of the picture. So you can see when their wavelength peak is within the same region, so you can see that within the same spectrum, you can see a peak of FBG, peak of normal FBG there. So these 2 grating must be spaced must be spaced closely together so that their temperature changes is uniform. So if the peak are not within the optimum range, the signal could not be detected. As you can see, the signal comes from the piezoelectric transducer. This is our vibration signal, comes from the signal generator. This is how the experimental setup. And then this is when the FBG and the FPI spectrum, when we subject it to different temperatures. So both peaks always within each other because both of them are placed closely together to ensure uniform temperature changes. Like I said before, if the peak are not within the optimum range, the signal cannot be detected. So this one, the peak are always within the optimal range. Okay, this is just the results, which is the top one. The red one is the from signal generator. So it is evident that the FBG FPI means the vibration sensor can detect the burst signal in 1 Hz, 2 Hz, and 3 Hz here. And then this the sensor also can detect in high frequency region, 3 kHz, 6 kHz, and 9 kHz. Okay, and then burst mode signal captured by the FBG FPI at different temperature. You can see we subject the sensor to different temperature, and it is evident that we can still detect the burst signal, right? And then this is the burst mode signal captured by FBG FPI at different temperature. This one is this is not burst mode signal. This is a high frequency signal captured by the FBG FPI. Pardon me. So it's a 3 kHz, 9 kHz, 6 kHz, and 9 kHz. You can see the blue one is at room temperature. The purple one is at 40 degrees C, and the red one is at 80 degrees C. You can see that the FBG FPI can detect the signal because we have tested that within if the peak is not within each other or the peak is not within the optimal range, the signal cannot be detected at all. Okay, as a conclusion, we have tested and fabricated a vibration sensor where it can measure, it still can capture the signal from the signal generator when it's subjected to different temperature. And then the further works that we are going to do, we're going to fabricate, we are going to test it with different materials so that whether the signal could be amplified or not. So thank you. That's all for me. Back to Dr. Aisha.
Thank you, Shamil, for your presentation. So I would like to open a question and answer session. Any question from the audience? Okay, I think that's all for this session. It's already in the early evening, so I think most of the people are sleepy or wait for going back home. So I will pass to Dr. Faiza for the closing remarks. Dr. Faiza, you can take over from here.
Okay, thank you, Dr. Aisha. Okay, I think for the past 2 days, we have gone through for so many presentations in this international conference. Actually, this, as mentioned by the chairman before, this is our second conference on the optical sensors, and then it is sponsored by MITE and also British Council. Before we close our conference today, we'd like to give gratitude and acknowledgement to all the people involved in this conference, especially the the community members, the chairman, which is distinguished Professor Dato' Haris Ahmad, and the secretary Leonard Bayam, and then we have 3 advisory committees, international advisory committees, Prof. Ken, Prof. Gilberto, and Prof. Aziz. And of course, we have the local organizing committee, Dr. Lim, Dr. Muhammad Zarif, Dr. Muhammad Khairul Anwar, and also Dr. Siti Aisha. And of course, all of these, the most hardworking will be these 2 people, which is our student, our PhD student and master student, who is Muhammad Ashraf alias. He's our secretary actually. He's also act as a program head. And then also to Muhammad Shamir bin Muhammad Saad as the marketing head. And then I have a request from the secretariat before we adjourn our conference for today. Can we open our camera so that we can take a snapshot of our participants. Shamil? Okay. Maybe you can arrange, Shamil, the, what do you call that? We can on our camera just for our memorabilia so that we can, and then I think before I forgot that the certificate will be given to all the participants by email. And we have all the attendance registrations. I think I was told by Muhammad Shabir that the teams can automatically capture who is the attendees of this conference. And of course, we will distribute the certificate based on the registrations that you have made through the Google Forms. So if, let's say, make sure that all the details are correct, especially your names and your affiliation and so on. So they will give all the certificates by email. By when, Shamil? Can you give some date?
Probably by next week. You can circulate the email.
Okay, if let's say if you don't get anything from us, you can just email us so that we can look at your case one by one. So hopefully there is no issue. Only this. Okay, Samir, you can lead the camera, the snapshot taking.
Okay, so I'll count to 3 and you guys post whatever you want to the camera. Okay, I just take a screenshot from my laptop. Okay, 1, 2, 3.
Okay. That's all.
Thank
okay.
you. Thank you very much.
I think this will not be our last conference. Hopefully we'll be organizing another conference next year. And I hope the participants will be even more. And then we can hope maybe not only restricted to 2 days, we can extend the conference for 3 days. That's our hope. Okay. Okay, that's all from us. And thank you so much for participating. And if let's say if there is some lag in our in us organizing this thing, so just ask for forgiveness lah. That's all. Thank you. Bye.